Hello everyone, this is Professor Bajigni. This is video of lecture 4. In this video I will finish talking about the material of chapter 3, then I will start on the material of chapter 4. In this section, resistors power rating, in addition to specifying the value of resistance of a resistor, power rating is usually specified. For this reason, resistors are rated in watts, specifying the power or wattage rating. The power rating of a resistor is the maximum power that it can dissipate without it becoming too hot or risking damaging to it. A resistor must have a wattage or power rating high enough to dissipate the power produced by the current flowing through it without becoming too hot. In this section, what it meant with the resistor power rating. When we buy a resistance and we need to install the resistance in the circuit, and I will show you an example, a practical example, how we use the resistor in a circuit to limit the current and to regulate the voltage. When we buy a resistance, two values we have to pay attention to. First, the value of the resistance. Is it like 100 ohm resistor or 1000 ohm resistor? And also how much power this resistance can handle. So when there is a current flowing in the resistance, we know one of the power formula to determine how much power dissipated or consumed by the resistance is I squared times R. So if we have a current flowing in the resistance 1 amp and we have the resistance value is 100, so 1 amp squared times 100, this is 100 watts. So that means when I buy a resistance of 100 ohm resistor value, I should specify to the seller that I need this value and I need also the resistance to handle 100 watts in terms of heat. So this is basically the meaning of the resistor power rating. So the word rating means either the ampere rating or the current rating, resistor rating or power rating or voltage rating. This means, the rating means that the maximum value that the machine or the device or the resistance can handle. So for example, if I buy a machine of 120 volt, so this machine requires 120 volt. This is what we call rating voltage. Or when you buy a machine of 1000 watt rating, that means this machine can produce 1000 watt, not more than that. That machine requires 120 volt rating. This machine, we cannot apply more than 120. Otherwise, this machine or this device will be damaged. So this is the meaning of the rating. Now, let me give you an example of how to design, for example, a circuit. Let's say I have a light bulb, small light bulb. Okay, this gives us a light. And I have this light bulb require 5 volt. But I don't have a supply of 5 volt. I have a supply of, for example, 10 volt. So this is a 10 volt supply. Now, if I do connect the 10 volt supply directly to the light bulb, this light bulb will burn out and it will be damaged. So what do I need? I need to insert or add a resistor here in this section here. I will draw the resistance. So I'm going to take off this line and then I will draw or add a resistor here. So that resistance R with a specific value, and I have to design the value of the resistance, depends on how much current flow and how much voltage required to be across the resistance. So adding this resistance is going to regulate the voltage, which means I need a 5 volt here, okay? But I have a 10 volt here, so I have to subtract, or I have to consume a 5 volt across the resistance in order to get a 5 volt across the lamp. Otherwise, as I mentioned before, if I connect the 10 volt directly to the light cannot handle this extra voltage, which means it's going to produce more heat and also produce more current, and that heat will damage the light bulb. So now when I design the resistance, let's say to 100 ohm, also I need to know how much current will flow through that resistance I. Let's say that the current is 2 amps. So now I need to design what is the rating power. So when I buy the resistance of 100 ohm, I need to specify what is the value of the power that I need to buy for that specific resistance. So again, one of the formula for the determining the power is I squared times R. So we know I is 2, so 2 squared times 100, that will be 400 watts. So when I buy a resistance of 100 ohms, I should also specify the rating power, okay, or the power rating of that resistance, which is 400 watts. 400 watts. So when I do buy the resistance, I will ask the seller to give me a resistance of 100 ohm value, and that resistance can handle 400 watts. Okay, so this is what it meant of the power rating. Okay, here's a good example to see whether this resistor, we have a resistor of 0.2 ohms, this is the value, and this is the watts. So again, always when you buy a resistance, you need to specify two things, the value of the resistance and the power rating. Okay, so now we need to be sure that if I buy this resistance, okay, this R resistance 0.0 ohm, and I allow a current of 8 amps. Now again, to have a complete circuit, I have to apply a power source here, plus minus, and I have to connect it to the wire. So if I allow an 8 amps flowing through the 0.2 ohms, I need to know how much power will be dissipated or consumed in the resistance. Now remember here, the type of the power, it will be converted into heat. So when there's a current flow through that resistance, it will produce power. The units of the power are watts. Now that watts, it will be in terms of heat. So now in this example, I need to be sure that this resistor is safe. It's not going to be damaged. Now to do that, I need to determine what is the power will be consumed or dissipated by the resistance of 0.2 ohms if 8 amps allow through that resistance. So again, apply one of the formula of the, this is the best formula here because we have ampere and we have ohms. So I is 8, so we square the 8 multiplied by 0.2. So that one will give us 12.8. Okay, this value is too high. That resistance was designed to stand or withstand 8 watts in terms of heat. Now, if I push too much current through that resistance, then the heat will be equivalent to 12.8, which is almost twice. So immediately this resistance will be on fire. Smoke will come out because the heat will be too much. This resistance cannot handle this amount of the current. Now in practice problem 3.5, we have to calculate the maximum safe current flow in 54 amps. So let's say, for example, I bought this resistor, it's 54 ohms, and I was told that this resistance can handle 4 watts. So I want to put this in a circuit. So what would be the safest maximum current that I will allow to pass through this resistor without damaging the resistance? Okay, it's very easy. We have resistance R, we have power. We know that one of the formula of the power is I square R. So the watts is given, the R is given, so it'd be easy to find I square. So we divide both sides by R. So this will be P over R. Now to find the current, we have to take the square root of both sides. So it will be I square root of I square, it's I, and square root of P over R. So then I would be equal to, P is 4 divided by 54. We take the square root, we find that the current will be, again, this is an ohm, so it will be 0.272 amps, or will be 272 milliamps. Okay, so now if I build the circuit and apply a voltage that gives us the current 272 milliamps, so the resistance will be safe. It's not going to be damaged here. Okay, so let me just erase this stuff here. Okay, efficiency. Efficiency is of a device or circuit is a means of comparing its useful output to its input. The law of conservation states that energy can neither created nor destroyed, but can convert it from one form to another. So efficiency, the meaning of the efficiency, that we have a machine, okay? That machine could be the dryer that dries our clothes, or could be the microwave, or could be the blender that we process our food. So we have an input power coming into the machine from the plug or from the power source. And then we have the motion or the heat. So this is the output, either a motion, whatever that machine will do. If it's a motor, that means it's a rotation. If it's a lamp, the output, it will be in terms of light. If it's a fan or it's an air condition, the output will be the cold air. If it's a refrigerator, the same thing. So we have an electrical input and then we have an output. Okay. So the efficiency is the comparison, how much output we get from the input. If I have an input of, let's say, 100 watts input to my machine, and I get 80 watts, so there's 20 watts being get lost. Where this 20 loss went, it will be as a loss. It will be power loss, they call it. It could be in terms of the heat, because any machine, will produce heat. Okay, let's say that we have a motor. That motor will produce heat. That heat is a loss. So it's an energy, but it's a loss. Also, there's a friction when you have a motor rotating. There's a friction. That friction will generate kind of losses. So there is a losses that will be wasted. So if we divide 80 over 100, we get 0.8 or 80%. So that means we said that this machine, it has efficiency of 80%, which means 20% of the input power will be lost. The only 80% will be useful power, will be converted into a kind of work in the output of the machine. So if the machine is a motor, so whatever that motor is doing is rotating and let's say heating the clothes or rotating the clothes inside the machine, or conveying some kind of rocks on the conveyor and so on. So this is the meaning of the efficiency. So efficiency is the ratio of useful output power to total input power. The amount of input, the input energy that an energy converting device can convert into a useful energy is its efficiency. Donated by the Greek letter, which is called eta. So eta here, let me see. So eta, sorry for that, I have to. So this is the symbol for the eta. In the process of energy conservation, part of energy or power is lost, as shown in the figure. So here's the figure here. Here we have a device, the device or a circuit. This could be a machine, could be a motor, could be a heater. We have an input power coming in, okay, which is basically, again, P is equal I times V. And then that machine will give us an output, and this output could be a motion, or could be a heat, or could be a cold air, okay, and so on. So some of the energy that, okay, some of the power or energy getting in is going to go as a losses, and we mentioned some of the losses could be the friction, or could be the heat that will be lost through the process in the machine, through the device, and so on. So this is the efficiency can be expressed in terms of power or energy. It's always less than 1 or less than 100%. In terms of power, so we have to know what is the output power, what is the input power multiplied by 100, and this is the percentage term. Now here we have the unit of the efficiency. It has no unit because power over power, both output power, input power have the same units. So then the units of the efficiency is nothing, is unitless, they call it. Okay. Now, we have to pay attention when we plug for this formula here, the units has to be the same. If this is, for example, if this is watts, this has to be watts. If this is kilowatts, this has to be kilowatts. If it's a horsepower, then the units has to be both either in horsepower or in watts. Now, coming back to this formula, so we know the power input, it has, because of the conservation of energy, the power input coming in, it has to be equal power output, which is we call the useful power, plus the loss, the power lost, or the power loss. Okay, let me go over this example here. Determine the efficiency of 110 volt motor that draws 15 amps. So we have a motor here, so draw a motor like this. Okay, that motor is connected to 110 volt, is going to draw a 15 amps. So we have the voltage across the load or the motor. That motor will develop an output. So usually an output is like a mechanical load. This will be like a mechanical. This will be a shaft, and shaft is rotating. How much power is lost? So we have the input. So we know the formula P in is equal P out plus P loss. Okay. Now we have Pn. So always Pn is V times I. Okay, which is 110 times 15, 1650. Okay, 1650 or 1650 watts. Now the output power, notes here, we are given the units of the output power, which is usually is the case. So when we have a mechanical power connected to the motor, usually that is a mechanical power, and the units they use is a horsepower. Now we know there's a conversion between a horsepower and watts. So 1 horsepower is equivalent to 747 watts. So before we plug in this formula to find P loss, because P loss will be Pn minus P out. Okay. So again, I'm going to write down the formula again here with large space. We have Pn equals to P out plus P loss. So if I want a P loss, so I move this to the other side, and it will become Pn minus P out. Okay, so again, I give in P in, P out. I can go directly and plug in this formula, 1650 minus 1342.8. So this is this is how much power this machine will be losing. Okay. Now to find the efficiency, again, this is the formula for the efficiency. P out, we have a P out, plug it here, over Pn, multiply by 100 to put it in a percentage. So there's an 81%. So this machine efficient, if almost 19% will be getting lost. Okay, let me solve the practice problem. The input power of a motor is 3260. So Pn is given. This is good. Pn. Again, I advise you to write down the formulas for the efficiency and for the power in, P out plus P loss. Keep them ready. And then we have the efficiency is equal to P out over Pn. Again, always the efficiency is less than 100% or less than 1 times 100%. Okay, having these two formula next to you, and some other thing that also you need to have it ready to you is the power law. P equal I times. So this is usually the input power. The input power is coming from this formula. This is the voltage applied to the load or to the machine, and this is the current flowing through the machine. So again, in this exercise, we are given the Pn, okay, Pn equal to 3260 watts. While its useful output power, so we are given also the output power will be 2450 watts. Again, look to the units here, it's good, same. So there's no need for the conversion. Calculate the efficiency, very straightforward. We have the efficiency is equal P out over Pn. P out is 2450 over 3260 multiplied by 100%. Okay, so again, you could use your calculator to determine the efficiency. We should get this number. Okay, another example here, example 3.7, an electrical motor develop a mechanical power. Okay, so always the mechanical power is an output power. So P out equal to 20. Now again, you have multiplied by 746 to convert it to watts. Okay, so this is the output power in watts. Calculate the efficiency, find the electrical input power. Okay, so we know that if with the efficiency 88%. So again, we use the same formula here. We have the efficiency is equal to, so the efficiency is given, so it will be 0.88 equal to P out over Pn. Now, since I convert the 88 percentage into 0.88, so there's no need for the 100%. Or if you keep it, 88, you have to take off you have to divide by 100. So we divide this by efficiency over 100, it gives us 88 divided by 100 is 0.88, and then we are having the output. So the input, so P input equal to, we do the cross multiply, so it will be P out over the efficiency. Okay, so it's P out over the efficiency. We just plug for P out, and for the efficiency, this is our output input power. So again, this is in kilowatt. Okay, so let me move to the next slide. Again, you could do this by yourself. Let me give you a hint. Determine the output power of an electrical motor that draws 8. So we have I equal 8 amps. So V is 220 volt. So I and V are given. So that means this is for our input. So when you're given I and V, this is the two quantities that we need to use to determine Pn. So again, I and V, they are not related to the output. Output also, it will be specified either in horsepower or in watts. So Pn would be 8 times 220. Okay, and it's 85% efficiency. So the efficiency is given at 85% or 0.85, either way. How much power is lost? Okay, and again, going back to the formula, Pn is equal to P out plus P loss. Okay, and then the efficiency equal to P out over Pn multiplied by 100%. Okay, so we are given Pn, we're given the efficiency, and we need to find P loss. So P loss equal Pn minus P out. Okay, that's good. So the only missing is P out. We already determined Pn. So what's the P out? P out, we can get it from this equation here. So P out would be, so we do the cross multiply, will be Pn times the efficiency. Okay. Again, so Pn will be 8 times 220. Let me move this, I have enough space. So Pn is 8 times 220 multiplied by the efficiency, which is 0.85. Okay, so this is a hint of how to solve the practice problem of 3.7. Okay, example here. This is a good example here for the for a DC motor. Again, if you look down here, this is the wire that goes into the DC motor here. This is the belt, and this is the load. Again, this could be the drum of the dryer that dries your clothes, or the washer, or the the coffee maker, whatever that that load, mechanical load here. Okay, something is rotating. So the information are given is the 12 volt, so the power supply is 12, and the I is 90, volt is 12. Again, from these two information, I can find Pn. So always Pn will be determined from the input on this side. This is our output side. It's energy coming in through the wires. Okay, so it will be 90 times 12. And then the output of the motor pulley is connected to a 1 horsepower. Okay, so P out is equal to 1 horsepower. Now again, we have to multiply by 7.6 to convert it to watts. Okay, what is the efficiency? Again, the efficiency will be P out over Pn multiplied by 100%, and you can use your calculator to determine the Pn and P out, and then easy to find the the efficiency. Okay, something here they call energy efficiency rating. The federal government tests products to ensure that the EER is correct, the energy efficiency rating. Electrical appliances are required to display their EER on product. Appliances means all the equipment that we use in our home, like the refrigerator, like the dryer, the washer, dishwasher, and so on. So these appliances. So when the government is testing those equipments to be sure that they are efficient, okay, because they don't want to lose energy, because when we lose energy, or not our energy, this energy is coming from the electrical power plant. The power plant, they are using, the gas, or using the oil, or using the coal. All of these fuel, they create, damage to our environment. So we need to reduce the pollution of our environment. So the government, they enforce the factories or the manufacturers to be efficient. Okay. So EERs are expressed as the percentage. The higher percentage, the more efficient the unit. The cheaper it is to operate, which means the unit will consume less energy. So again, if we buy a high efficiency device or a machine, then our machine will use less energy. And if the machine consumes less energy because it's high efficient, that means we are going to reduce the dollars, the thousands of dollars, and over several years of use, and also we are going to save the earth from the pollution. So this is the end of the chapter 3. Now we move to chapter 4. Chapter 4 is about series circuits. So far in the previous chapters, we have covered circuits to have a singular resistor. From now on, we will consider circuits with more than one resistor. Such resistive circuits can either be in series or in parallel, or neither. A simple example of a series and parallel circuit are shown in the next two slides. We will consider how to analyze series circuit in this chapter, while we will deal with the parallel circuits in the next chapter. Circuits that are neither exclusively series nor parallel will be covered in later chapters. So just I want to explain the meaning of the analyzing circuits. The analyzing the circuit, it meant here, analyzing circuit. When we say analyzing circuit, it meant we need to find what is the voltage across each element in the circuit. For example, if we have 2 or 3 resistors, we need to know what is the value of the voltage across each of these resistors. Also, I need to calculate and find the value of each current through each resistor. Also, I need to calculate what is the value of the power dissipated by each of these resistors. So this is the meaning of analyzing the circuits, whether series circuit or a parallel circuit. In the series circuit, there is only one path over which the electrons or electric current can flow. If we look to figure 4.1, we have, this is one of the light bulb, this is the second one. So if we connect them in this manner, we have the current will flow in through the wire and then go inside the light bulb and then come out and go inside the light bulb and then come out and go through the switch and go back to the other end of the battery supply. Same thing here. We have the batteries, the current flow, go through this wire here from the back and then coming into this point, go inside, coming out, go inside the second light bulb, coming outside, and then go inside, coming outside, and go to the other side of the terminal. So we could see here, no matter how many of those components of those light bulbs are there, the current is the same. It's flowing in one path. So this is the definition of a series circuit. When the elements are connected in series, it meant that they are having the same current flow through them. Now, if we give you another example, let's say this is a resistor 1, resistor 2, 3, and 4. So if this is R1, R2, R3, R4. So as you notice here that the connection, there is one connection between R1 and R2. Later on, we call this as a node. There's another connection here. So when we connect this end, this is the first end, could be connected to something else. Now, the second end of this resistor will be connected to the first end of this resistor here. And then the second end or terminal of this resistance R2 will be connected to the first terminal of R3. And then second terminal of R3 will be connected of the first terminal R4. So as if we apply a current through R1, the same current will flow through R2, R2, 3, and R4, and then comes out and move back to the power supply. We begin in the chapter by first introducing the basic concepts of nodes, branches, loops, series, and parallel. We then learn what series circuits are. Next, we introduce Kirchhoff's voltage law, which along with Ohm's law is very useful in analyzing the circuits. Again, we come back to the word analyzing circuit. As I mentioned, it meant we need to find, for example, how much voltage across this lamp, across this lamp, across this lamp, how much current flow on this one, as well as this one. And since they are the same, so it will be the same. And how much power each of this lamp will produce as a light. We discussed voltage source in series, voltage dividers. There's another thing that we need to discuss, and power in series circuit. So again, this is the topics of the series circuit. Okay, what are nodes and branches and loops? Circuit elements can be interconnected in a multiple ways. To understand this, we need to be familiar with some network topology concepts. A branch represents a single element, such as a voltage source or a resistor. A node is the point of connecting between two or more branches. A loop is any closed path in a circuit. Okay, let's talk about the nodes. A node is usually indicated by a dot in the circuit. Okay. Although we do not follow this convention in this book. So what it meant here, if we look to these three dots here, these three dots here, they are not three nodes. They're only one represents one node. The same thing for the bottom one here. So the top one, three nodes or three dots, they are not necessarily three nodes. This is only one node. This is a node. Now, what is the difference between these three dots and this dot? Why we call this as a node and these three here, only one of them or only one represents only one node? Because if you look to this point or this connection or this node and this one, there's in between these two, there's an element, which is the 10 volt. So in this case, this is called a node, this is called a node. But this one here, since there's no element in between, so this dot is the same as this node, and this dot is the same as this node. So all these four here, they represents one node. The same thing here, we have an element between this point and this point. So therefore, this is a node, this is a node. But since there is no an element between these two here, so this is only one node. Same thing for these two here. Same thing for these all three. So all three here represents one node. So now this node here and these nodes, these are two nodes because there is an element in between here. Same thing here, it's an element. So how many nodes we have here? We have 1, 2, and 3 nodes. If a short circuit wire connected two nodes, the nodes are considered as one. So again, this is, you can consider this like a short line, short circuit. So this is considered to be one node, this is considered to be node. Or as I said, if there is no an element between those two dots, so that means this is one node. The circuit shown has 3 nodes. Keeping track of nodes is an important part of the circuit. This is very important. Later on, when we come to analyze the circuit, we will use one of the techniques they call the nodal analysis. Okay, so again, this is the recognizing the node, as I said. So this is, you don't have to put dots in each of this here, since this is one line, this is a line, or this is a short, or there's no element in between these points or these dots. So this is another way of how to recognize the nodes. Network topology, a loop is independent if it contains at least one branch not sharing by any other independent loop. Now again, this definition might be a little bit difficult, but I will explain to you an easy way. What is the loop mean? A loop mean is a closed circuit. Okay, this is a closed here. Okay, closed. This is okay. So this is a loop. This is a loop. This is a loop. I'll show another loop. This is also a loop. Okay, because it's a closed path. This is also a loop. Okay, this is also a loop. Okay, so a loop basically is a closed loop, it's a closed path. Okay, two or more elements are in series if they share a single node. As I mentioned earlier, they share a single node. Okay. The other node here is not shared with any other. Okay, so this is shared nodes. Again, the other definition of a series is that the current is the same. Okay, current flow in every element, series element are the same. Okay, two or more elements are in parallel if they are connected to the same two nodes and thus have the same voltage. Now, this one, it's obvious they are series because they are sharing only one node. And also the current is the same. Now, for this here, see this, okay, this has a node, this is one node here, this is one node. So they share, for some reason I couldn't. Okay, so if you look down here, this is one node, this is one node. So both of them, they share two nodes, while in here they share only one node. R1 and R2, they're sharing one node. R2 and R3, they share two nodes. Also, if we apply a voltage here like 10 volt, the 10 volt here, it will be the same across this voltage, going to be the same across this resistor, same across this. So they share the same voltage and they share two nodes. Okay, let's look to this example 4.1. Determine the number of branches and nodes in the circuit shown in figure 4.4. Identify which elements are in series and which are in parallel. Okay, again, okay, let's forget about looking to this original circuit here. So this is a node and this is a node. Why? Because there's an element in between. And also this is a node because there's an element, 5 ohm element in between. Now, how about this? Is this a new node? No, because this is a line here. The other thing that since there's no element here in between, so these two here, they are one node. Okay. Same thing here. This is a dot here. Is this a new node? Is this a new node? The answer is no. Okay, because they are, since you can draw a line and there is no element in between, you can short all these 3 points. So that means all three here are 1 point. So this is one node, this is one node, this is one node. So we have 3 nodes, and the element, just count how many elements we have, either a voltage or a resistance. So we have 1, 2, 3, 4 elements, 1, 2, 3, 4 nodes. Okay, going back just to answer the question. So these two here are in series because when the current coming out goes in both of them same. Also, they share one node. Okay, the other node of 5 here is not being connected to this node here, so we couldn't say that they share two nodes. Okay, now for this one, we have a node here, and we have a node. So this 12 volt here is going to be also across the 6 ohm. So the same voltage across both of them, so they are in parallel. Also, they are sharing two nodes. This node and this node. Again, practice problem 4.1. How many branches and nodes does the circuit in figure have? Now, if you look here, branches, okay, let's look to the node. This is a node. Again, this is a second node. No, I made a mistake. It's not a second node, same node here. Since there's no element in between, that means this is one node. Good. Okay, this is another node. Is this another node? No, same node. Second, two. How about this? We know this is a node because there is an element between this point and this point, but how about the other here, other three? Are they different nodes? No, they are not. Since we can draw a line, we can show them. And also since there's no element in between, if I put an element, this become a node, this become a node, this become a node. But since there's no element, so the three of them here, actually the four of these dots or connections, one node, one, second node, third node. Elements easy to count, 1, 2, 3, 4, 5. Okay. So we have 3 nodes and 5 elements. Okay, series resistors. So as I mentioned earlier that in the previous chapter, we only study a circuit with only one voltage source and one resistor. Now we need to see if we have more than one resistor. Either they are connected in series or in parallel. Now, how to analyze the circuit? How to find the voltage, for example, V1 across the R1? How much voltage that this resistance will consume? And how much voltage this resistance will, how much current will flow through this one, and how much current will flow through this, how much power, P1 for example, dissipated or consumed by R1, and how much power P2 consumed by R2. So to do that, we need to find what is the total resistance here. So because when we apply a voltage to these two resistors, both of them, they're going to oppose the flow of the current. So the current will be less than if I have only one resistor. So if I have only R1, so the current I will be more than if I have R1 and R2 in series, because more resistance will try to reduce the amount of the current through the circuit. So if we have two resistors, so it's very easy to determine what is the R total, or sometimes they call it R equivalent. They call it equivalent resistance. Okay, or equivalent resistance. So either total resistance or equivalent resistance, and the abbreviation for that is REQ. So REQ is the same. So some books, they use REQ or R equivalent. So again, it's very simple, very easy to determine what is the total resistance that is going to oppose the current I. It will be R1 plus R2. So for example, if I have R1 equal 5 ohms and R2 equal 10 ohms, so RT will be equal to R1 plus R2 will be 15 ohms. And then after that, I can apply Ohm's law to find the total I that goes through both of them. Now, in general, the total resistance equals the sum of the resistance. So again, if I have more than one, up to let's say n is the number of the elements, number of the resistance. So if half n is 5, so that means it will be R1 plus R2 plus R3 plus R4 plus R5. So n is the number of the resistor. So n equivalent to the number of resistors, okay, connected in series. Okay. 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 So after we find the RT, and then we'll show you how to use Ohm's law to find I. And then after that, then we apply Ohm's law across each component. Okay. So I'm going to draw the circuit, the previous one. So here's R1, here's R2, here's V1, here's V2, plus minus, plus minus. So, so now after we find I, after we find RT, okay, let's say we find RT is equal to R1 plus R2. I will explain this in the coming slides more. And then we have the voltage here, the voltage supply, V here, V, and apply Ohm's law, so I will be V over RT. So I, whatever the resistor, let's assume V is equal to 50 volt, and let's assume R1 equal to 5 ohms, and R2 equal to 15 ohms. So we need to find RT, so RT is equal R1 plus R2, so it will be 5 plus 15 is 20 ohms. Now I need to plug for the I, so I plug for I in this formula. Again, we get this from Ohm's law. We know that Ohm's law V is equal I times R. Now R, since we have two of them and we combine them, they become one. Okay, one resistor RT. Okay, so I would be equal to V over RT again. So V is 50 and 20, so it will be 2.5. Okay, so after finding I will be able to find V1 and V2. Now this is the process of analyzing the circuit. As I mentioned earlier, that analyzing the circuit, it meant we need to find the voltage and the current and the power in each element of the circuit. So we did find I. Now what is I through the R1? It's 2.5. What is the I through the R2? It's 2.5. Why? Because the I is the same. Why? Because these two resistors, R1 and R2, are connected in series. And the definition of the series circuit that current is the same through all the elements in the series circuit. So I is the same here in the voltage supply. I is the same in the R1. I is the same as the R2. So we have the current is looping or rotating through the circuit. Okay, so let me erase this one here and let me write down the I. So we get I is equal to 2.5 amps. Again, if we need to find V1, so V1, it will be I times R1, which is here. So I is 2.5 and 5, and then this will be 2.5 multiplied by 15, this will be the voltage drop. Now, if you do your calculation, you will find that V1 plus V2 must equal to the supply voltage. Supply voltage must equal to they call it the voltage drops. This is called voltage drops. It will be defined here. This indicates that the voltage drops across each resistor depends on its resistance. because I is the same, so it depends on what's the value of the R1, it will give us the value of V1. So these voltages, V1, V2, and V3, and Vn up to Vn, are called voltage drops. Okay, voltage drops across the resistors. The voltage supply always must equal to the total or the sum of the voltage drop, and this topic will be discussed later. Okay, now, as I mentioned earlier, this is a process of the circuit analysis. So we need to know what is the power dissipated in a series circuit, how to examine. So we know that, again, we're coming back to the general formula of the power. We have I times V, we have I squared times R, we have V squared over R. Okay. Now, since we are finding the power in each element or each resistor, R1, so since if I know the current through the R1, and if I know the resistor value, then P1, this is the power dissipated through the R1 or in R1, will be I squared times R1. If I have second resistor, it will be I squared times R2 and so on. So as you notice here that we have to use the current through that resistor, we squared, and also the current through the resistor number 2, R2, in order to determine the power dissipated in each resistor. Now again, the same thing as we mentioned, that the supply voltage must equal to the voltage drops. The same thing, the power, the total power, PT, which is the power delivered to the series circuit, the power that coming out from the power supply, must equal to the power dissipated or consumed by the resistors. Okay, so PT, the total power, has to be equal to P1 plus P2 plus B3 plus P4. So depends on how many resistors we have. So let's say we have 3 resistors in series. So PT will be equal to P1 plus P2 plus B3. Now, how to find P1? Again, P1 is equal I squared times R1. P2 is I squared times R2. And P3 is equal I squared times R3. Now, if we plug this PT equal to P1, here's a P1, is I squared times R1, plus P2, I squared times R2, plus I squared times R3, is we factor out, if we take I square out, so PT equal to I squared, and then R1 plus R2 plus R3. Now, if you remember, we defined the R1 and R2 and R3 is the RT, our total. So if we add R1 plus R2 plus R3 plus R4 and so on, this is the RT. So this is R3. Okay. So again, this will be I squared RT. So if I know RT, and I know the current, then if I square it, multiply by RT, I get PT. Or I could use the individual power consumed by each. So if I know RT, I will be able to find PT without getting to find individual power loss in each resistor using I squared times RT form. I'm going to stop on this slide here for the next lecture. And thank you for your watching. And I'll see you in the next tape, next video.